Do. Hello, hello, hello. Oh, that unknown user followed me yesterday. Alright. Yesterday we did chapter 4, or chapter 3. Today we're doing chapter 4. And I don't know why. Here, let me refresh this. There we go. Is this Alright. I think this is the first video.
TCP/IP model, the topmost layer. So hello everyone, this is week 5 and we start with another new chapter in this week, which is chapter 4. And in this chapter,
Wait, hold on. Let me make this smaller. Alright.
we are going to cover the third layer, the third layer from the top of the TCP/IP model. The topmost layer is application layer, then transport layer, and it is actually, we can call it as the middle layer, the network layer. Network layer is a huge layer and it has a lot of functions to do. So starting from this week until week 7, and even after the midterm exam, we are going to continue with the network layer because it's a huge layer. It has many functions, many responsibilities and many functions to perform. This layer is a combination
What the hell?
of both hardware and software. The topmost two layers, application and transport, they are purely software based layers. Network layer is a combination of both hardware and software, and the bottommost two layers, which is the data link layer and the physical layer, they are the purely hardware layers. So let's start with the network layer. In this chapter, first of all, I will discuss what are we going to discuss in this chapter. And today, in this week, in this class, what I am going to cover. So these are all the things that we are going to cover in chapter 4. It's not like we are going to cover all these things in 1 or 2 weeks. We will be covering few things before the midterm, and we will be covering few things after the midterm. So in this week lecture, I'm going to cover 4.1, which is introduction, 4.2 virtual circuit in datagram, 4.3 which is what's inside a router, and in 4.4 I'm only going to cover until the datagram.
Alright, get to the point.
From introduction, middle layer of the TCP/IP model. It is responsible for transporting the segment from the sending host to the receiving host. So it works from host to host, whereas our transport layer works from process to process. It works, transport layer works between the processes, whereas network layer works between the host. Now if you it transports the segment from sending to the receiving host. Now on the sender side, it encapsulates the segments which it receives from the network layer and forms a datagram. So it encapsulates the segments received from the network, from the transport layer, and forms a datagram. And on the receiver side over here, it decapsulates the segment from the datagram and delivers the segments to the transport layer. So on receiving side, it decapsulates the segment from the datagram and then delivers those segments to the transport layer. Network layer protocol is everywhere in host and the router. So if you see over here, our intermediate devices, the network core, which we call it as the network core. Network core works only on 3 layers. The upper 2 layers, transport and the application layer, are not present in the network because simply transport and application layer, they consist of the applications which are used by the end user. So if you see over here, our network core only contains the bottom 3 layers, which is physical layer, data link layer and the network layer. Now what does the router does in the network layer? Router examines the header fields in all the IP datagrams that it receives and which pass through it. So by examining the header, it decides which output port a particular datagram should be directed to so that it can reach to its destination. Alright, so if you see over here the animation, so it goes and then it is delivered over here. This is how it works. I show you again. So for example, you make a message, it goes to network layer, then it goes to all these links and then from the network layer to the application layer. Alright, moving ahead. Two important network layer functions are forwarding and routing. Already although we discussed about it, I think in chapter 1. Forwarding is moving the packets from the router's input port to the appropriate router port, and routing is to determine the path, the shortest path or the perfect path between the source and destination so that that path can be taken by the packets. Now for routing, we use certain routing algorithms which we will be talking about later in this chapter. So forwarding is routing is like it's a process of planning a trip from place A to place B. For example, you come to the college, so you plan a trip, you plan a path, you take a path from your home to the college. So that is called as routing. Now while you plan your trip, there may be certain areas you have to pass through. For example, you may have to pass through Khalij, you may have to pass through Jalmuda, or you may have to pass through certain other district. So passing through those districts, that is called as forwarding. That means you enter to a district, you leave that district. That is called as forwarding. So process of getting through single interchange, that is called as forwarding. So routing is the complete path or the process of complete trip from source to the destination. For routing, of course, we use the routing algorithms. We are going to talk about it later in the slides. So how does the router decides about the forwarding? So routing algorithm actually determines the end-to-end path through the network, and forwarding table, this is the forwarding table, it determines the local forwarding at the router. So the basic purpose of the forwarding table is to determine the output port to which the packet should be directed to. So for example, let's assume that this packet arrives at this router at a particular point. So when this packet arrives at the router, what this router will do, it will examine the header, and when it examines the header, it finds this number 0111. Now when it finds this number, it consults
This isn't my
it to
notes, so I have no
forward it.
idea.
There is it will forward it, or connecting with the routers, they must establish the virtual connection or the logical connection, but it is not always the case. If we are using the virtual datagram, then only the virtual connection is established. If we are using a datagram, a virtual circuit network is used, then virtual connection is established. If we are using a data involved of the where it will in transporting or in sending the datagrams from sender to the receiver. So what are the services a network layer is providing?
Wait, it just skipped over all this other stuff. Let me see. Data plane, local, per router. Ooh. Data plane is local per router function, determines how datagram arriving on router input port is forwarded to router output port, control plane, two control plane approaches. So if that's a question, that could be a question. What are two control plane approaches? I would just say traditional routing algorithms and SDN. Implemented in routers, implemented in remote servers. Alright. Data plane. What is this? Network layer. Where does the network layer consist of? Data plane and control plane. Data plane, local. Control plane, network. So the local's input to output for forwarding. Datagram is. Wait a second. I get it. So this is the datagram. I mean the data plane, and the routing is the control plane. And the routing algorithms are these two things. So data plane is local, determines control plane is network wide. Alright.
The first service that the network layer provides
Wait a second.
is the services. The services provided by the network layer in transporting or in sending the datagrams from sender to the receiver. So what are the services a network layer is providing? The first service that the network layer provides is the guaranteed delivery. Guaranteed delivery is a service which makes sure that the packet will definitely arrive at.
That's what I got tagged in. I was wondering what the hell I got tagged in. Alright.
At the destination. So this makes sure that it guarantees that the packet will definitely arrive at the destination. Second is guaranteed delivery with bounded delay. There can be some delay, but packet will arrive. So this service not only it ensures that packet will arrive, but it will arrive within a specified certain host to host delay bound. For example, it can be 1 millisecond, it can be 100 milliseconds. So some delay bound is specified for the packet. There are other services also which are provided to flow of packets between the source and the destination, which is in order packet delivery. So this service of the network layer, it guarantees that packets arrive at the destination in the order that they were sent. So for example, source sends 5 packets, 5.
Wait, hold on. Hold on. Alright.
Packets, which is in order packet delivery. So this service of the network layer, it guarantees that packets arrive at the destination in the order that they were sent. So for example, source sends 5 packets, 5 packets, 1, 2, 3, 4 and 5. So this service ensures that the packet will arrive in the order of 1, 2, 3, 4 and 5 and not as 3.
These are the weirdest fucking numbers I've ever seen, if I've seen one.
5, 2, 4 and 1. Next is guaranteed minimal bandwidth. So this service of the network layer, it emulates the behavior of the transmission link of a specified bit rate between the two hosts, between the sender and the receiver. So it makes sure that the minimal bandwidth, whatever is the minimal bandwidth provided by the transmission link, is always provided between the sender and the receiver. So as long as the sender host transmits bits rate below the specified bit rate, no packet is lost. And when each packet arrives with a specified, for example, whatever the bit rate is specified, it arrives within a pre-specified host-to-host delay within the 40 milliseconds. So it guarantees.
I hope he doesn't ask for all 5 of these, or all of them. I need to remember guaranteed delivery and order. I could remember like 3 of these, probably. Security, guaranteed minimum bandwidth, and order datagram delivery. But that's not guaranteed.
Guarantees the minimal
We'll
bandwidth.
soon find out down here.
Next is maximum jitter. So basically, what is a jitter? Jitter is the delay in the subsequent uh, is delay in the arrival time of the subsequent packets. Many times you might have noticed or you might have experienced while you are downloading a video or you are watching a video, it plays for a while, then it stops and the cursor just revolves, and then after a while it plays again. So that is called as jitter. So maximum jitter, it guarantees that amount of time between the transmission of two successive packets, destination 5 minutes amount of people at the receiving side potentiality. So this was only a few.
Yeah, that one was kind of short. We didn't need to really know much for this beginning part. This one's shorter. I mean, I say shorter, it's still 2 different videos here. Both 58 minutes long. Alright, so no guarantees, best effort, service model, timing or order of delivery, because it just says in order datagram delivery, bandwidth available to end and end.
Services that a network layer can provide. Although there are many other variations possible, network layer can provide much more services than what we have discussed now. Let's move on to the next topic, which is what's inside a router. Alright, so let's discuss over here the components of a router. The components of a router. What are the components of the router? There are four main components of the router, which are input port, output port, switching fabric, and a routing processor. So what are these components, and how do these components interact with each other? Let's talk about this. Going ahead. So as we know, the two main important functions performed by router are routing and forwarding. So routing is providing a path between source and destination for all the packets, and forwarding is transmitting the packet from the router's input to the router's output port. So forwarding the datagram from incoming to the outgoing link. So if you see over here, we have this is the switching fabric at the center, then there is a routing processor, and then there are input ports and the output ports. So this is how the internal structure or the internal architecture of the router looks like. Let's understand the function of each part in detail. Alright, so forwarding tables, they are pushed to the input ports, and this is the forwarding data plane, right? So let's first of all talk about input port. Now input port, it performs many functions. It performs the physical layer function. It performs the physical layer function of terminating an incoming physical link to a router. It can perform the data link layer function also, which is needed to interoperate with the data link layer. It also performs the lookup and the forwarding function. Alright, so let me first of all discuss one by one. It performs the physical layer function. Okay, if I go back to the diagram, physical layer.
This is where this chapters where like the notes are all fucked up.
Function. Do you see over here? We have in the input layer, we have different boxes colored and their different sizes. So it performs the physical layer function. So if you see the leftmost box, this one, the small green box on the input port, and the rightmost box on the output port. So it performs the function of the physical layer function. It also performs the data link layer function, which is represented by the middle box in the input and the output port, and it also performs the lookup and the forwarding function. So it is represented by rightmost port in the input port and the leftmost box in the output port, which is the red color box.
Hold on. What the fuck did Peso? What is this? Goddamn Coast got me distracted. When did this drop? 2 years ago.
bad bitches, Lonnie Karma, where they at? Hey, hit the dance on them. Two bad bitches with some ass on them. I feel like we're willing to throw the cash on them. I ain't gonna pass on them, but I might just crash on them.
I like the I like the hook. Is this what you wanted?
Core network layer. In the last week's lecture, we covered.
That's wrong video.
Basically, it performs the lookup and forwarding function so that the packet can be forwarded into the switching fabric. So, packet can be forwarded to the switching fabric of the router and it emerges at the appropriate output port. Then, control packets, for example, packets which carry the routing protocol information, they are also forwarded from input port to the input port to the routing process.
Wait, why did she say that as if they weren't?
Represented by most box, the leftmost box, this one, the small green box on the input port, and the rightmost box on the output port. So it performs the function of the physical layer function. It also performs the data link layer function, which is represented by the middle box in the input and the output port, and it also performs the lookup and the forwarding function. So it is represented by rightmost port in the input port and the leftmost box in the output port, which is the red color box. Basically it performs the lookup and forwarding function so that the packet can be forwarded into the switching fabric. So packet can be forwarded to the switching fabric of the router and it emerges at the appropriate output port. Then control packets, for example, packets which carry the routing protocol information, they are also forwarded from input port to the input port to the routing processor. So in practice, multiple ports, they often gather together on a single line card within a router. So if you see, input port performs many functions related to the physical, related to the data link layer, and related to the forwarding and the lookup function. Next we talk about switching fabric.
The hell?
Okay, so let's talk about routing processor first, as given over here. Routing processor, as we know that processor.
Thing is, I know I've seen control plane, is that all it's called?
Processor is always the main part. So routing processor is running the routing algorithm, which is implemented as a software to produce the forwarding table. Called as
See, the thing I'm afraid of is he's gonna ask, what is generalized forwarding? And I'm just gonna not know. Oh my god, I'm so stressed.
routing or the management control plan. So it is executing the routing protocol, it maintains the routing information, forwarding table, performs network management functions within the router. So processor is again the heart of the routing processor. A copy of the forwarding table is distributed to the input port, which is also done by the routing processor. Forwarding table. So forwarding table is nothing but a routing table. It is used to specify the path or the output port for each incoming packet based on the header of the packet. Input port function. So this is what I told you. It performs the physical layer function, which is equal to the bit level reception. The middle layer performs the data link layer function, for example Ethernet, receiving the protocol, and the last performs the looking, forwarding, and the queuing function. So it's a decentralized switch. So giving if the datagram destination is given, it will look up the output port using the forwarding table in the input port memory. And if datagram arrive faster than the forwarding rate, it has to queue the datagrams into the memory of the router. Okay. Now let's talk about switching fabric. Now what is a switching fabric? Switching fabric.
Crazy part is, I have these notes. I think my professor, because like we have the longest prefix thing here, and then we have these notes, so it's
Actually connects the router's input ports to the output ports. If you have seen in the diagram also, so this high speed switching fabric, it connects the router's input port to the output port. This switching fabric is completely contained within a router, a network inside of a network router. So there is a network inside of a network router. So basic function is to transfer the packets from input port to the appropriate output port. Switching rate, it's the rate at which packets can be transferred from input to the output port. Now there can be three kinds of switching fabric. It can be a switching via memory, it can be a switching via bus, it can be a switching via crossbar. Now let's understand what's the difference between them. Switching via memory.
she says crossbar.
Memory switching crossbar. Now let's understand what's the difference between them. Switching via memory, switching via bus, and switching via crossbar. So switching via memory, they were the first generation routers.
Hold on. I know this might be a question. Three major types of switching fabrics: memory, bus, and interconnection network. I need to remember that last one. Memory bus and interconnection memory or network.
And the
See, I'm already
earliest
messing up.
routers were often traditional computers with switching between input and the output port, which was done under the direct control of the CPU. So the traditional computers with switching under direct controller of CPU. Now in this input and the output ports, they functioned like a traditional input-output device, and the input port with an arriving packet is first signal the routing processor via interrupt. So what happens is, when the packet arrives, packet is first of all copied to the system's memory, which is the memory. Then CPU extracts the destination address from the packet's header, looks up the output port into the forwarding table, and then copies to the output port, then copies that datagram to the output port. So if you see over here, when it arrives, it is stored into the memory. First of all, packet is copied to the system memory. Now CPU will extract the destination address from the packet's header. It will look for the output port and then it will copy it to the output port. If you see over here, like this. But the basic drawback is speed is limited by the memory. So if it's a high speed,
That could be, bro, there's only like 24 questions, but that could also be a question. Like, what's the drawback? What's that drawback of switching via memory? Oh my god. Speed limited by memory's bandwidth. I need to remember that. Speed limited.
memory, speed will be faster. If it's low speed memory, speed will be slower. And another is only one packet can be transmitted at a time. So that was another disadvantage. Alright, so coming to the next, which is switching via bus. So what happens in this, let's understand. Okay.
And this one's limited by the bus bandwidth. Bruh, all of these are just limited.
So in this switching technique, input port transfers the packet directly to the output port over a shared bus. So if you see over here, this is the input port, this is the output port, and both of them, they are connected through a shared bus. So input port, they transfer the packet directly to the output port over a shared bus, and there is no intervention of the routing processor. Although the routing processor is not involved.
What's the difference between... Okay, so this copies to the memories. Hold on, let me go back to what she said about the memory.
Via memory, it can be a switching via bus, it can be a switching via crossbar. Now let's understand what's the difference between them: switching via memory, switching via bus, and switching via crossbar. So switching via memory, they were the first generation routers. The simplest and the earliest routers were often traditional computers with switching between input and the output port, which was done under the direct control of the CPU. So the traditional computers with switching under direct controller of CPU. Now in this, input and the output ports, they functioned like a traditional input-output device. And the input port with an arriving packet is first signal the routing processor via interrupt. So what happens is, when the packet arrives, packet is first of all copied to the system's memory, which is the memory. Then CPU extracts the destination address from the packet's header, looks up the output port into the forwarding table, and then copies to the output port, then copies that datagram to the output port. So if you see over here, when it arrives, it is stored into the memory. First of all, packet is copied to the system memory. Now CPU will extract the destination address from the packet's header. It will look for the output port and then it will copy it to the output port. If you see over here, like this. But the basic drawback is speed is limited by the memory. So if it's a high speed memory, speed will be faster. If it's low speed memory, speed will be slower. And another is only one packet can be transmitted at a time. So that was another disadvantage. Alright, so coming.
So there's two disadvantages. Memory is... Speed is limited by the memory, the bus is limited by the bandwidth, the memory can only do one packet at a time.
To the next.
Alright, so they both these can do one packet at a time.
Which
right?
is switching via bus. So what happens in this, let's understand. Okay, so in this switching technique, input port transfers the packet directly to the output port over a shared bus. So if you see over here, this is the input port, this is the output port, and both of them, they are connected through a shared bus. So input port, they transfer the packet directly to the output port over a shared bus, and there is no intervention of the routing processor. Although the routing processor is not involved in the bus transfer because the bus is shared, but only one packet at a time can be transferred over the bus. So only one packet can travel on this bus. A packet arriving at the input port and finding the bus busy with the transfer of another packet is blocked from passing through the switching fabric, and it is queued at the input port. Suppose packet 1 arrives. Packet arrives, it sees that there is another packet which is being transmitted on the bus. So this packet will not be transmitted unless and until the packet before it is transmitted fully to the output port, and in this scenario the packet which has arrived now, it will have to wait, it will be queued up. Because every packet must cross the single bus, switching bandwidth of the router is limited to the bus speed. So again, switching is limited by the bus bandwidth, and that is one packet at a time can cross the bus. The last technique is switching via crossbars. So we also call it as switching via interconnection network. So this is actually a way to overcome the bandwidth limitation of a single shared bus. So the basic idea is to use a more sophisticated and advanced interconnection network, similar to those that have been used past to interconnect the processor in a multiprocessor system. So what is a crossbar switch? If you see over here, this is a crossbar switch. This is a crossbar switch. A crossbar switch, it's an interconnection network consisting of two N buses and that connect N ports to N input ports to N output ports. So in this case, number of input ports is same to the number of output ports, but the number of buses are 2 times N. 2 times N. What does 2 times N means? If there are N input ports and N output ports, number of input ports should always be equal to number of output ports. Then the number of crossbars, or we call it as number of buses, should be 2N. For example, over here, number of input ports is 3, number of output ports is 3. So what is my N? N is 3. So in this case, the total number of interconnections, or we call it
that makes sense,
as total number of bus should be 2 multiplied by 3, which is 6. Let's calculate number of buses.
It's 6, I don't know.
Let's check number of buses. If you see, this is the first bus, second bus, third bus, fourth bus, fifth bus, sixth bus, right? And total number of interconnection point should be N square. If you see interconnection point 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is N square. So number of interconnection points is N square, and number of buses is always 2 multiplied by N. So what is the general idea behind it? The general idea is, when a packet arrives at the input port, it travels along the horizontal bus, which is, if you see, horizontal bus attached to the input port until it intersects with the vertical bus, leading to the desired output port. So if for example packet 1 arrives and it wants to go to X, it will travel on this horizontal bus and until it finds the intersection for the desired output. So this is the intersection, or intersection with the vertical bus, which leads to the desired output port. If the vertical bus leading to the output port is free, now if this bus is free, then the packet is transferred to the output port. But if the vertical bus is being used by someone else to transfer the packet from another input port to the same output port, then the arriving packet is blocked and it must be queued in the input port. So let's check with this example which is given over here. So for example, when a packet from port 5, so it when solar buses aimed as, so if it be reading the
Oh my god.
output port.
So input, alright, let's go over this because I don't know what she was doing. Switch fabric. Slower than queuing may occur. That's fine. Head of the line. Blocking. Queue datagram. What's this? What happened? Output port contention. Only one red datagram. Queue datagram at front of queue prevents others in queue. That's, I would say, self-explanatory, but I don't know.
Let's discuss about it. So what does the output port does? Output port stores the packet that have been forwarded to it through the switching fabric and then transmits the packet on the outgoing link. The output port performs the reverse functions of the input port, or it performs the reverse function of the data link physical layer functions at the input port. But when the link is bidirectional, an output port to the link will typically be paired with the input port for that link. So if you see, it buffers, it queues, then it sends, then it terminates. So buffering is required when datagrams arrive from the fabric faster than the transmission rate. That's why the buffering is required. So in the input,
I feel like, what? Buffering required when datagrams arrive from fabric faster than link transmission rate. Which datagrams drop if no free buffers? Because that's like the free buffer space, right? Priority queuing, who gets best performance, network neutrality, scheduling discipline.
so if you see, it buffers, it queues, then it sends, then it terminates. So buffering is required when datagrams arrive from the fabric faster than the transmission rate. That's why the buffering is required. So in the input port, queuing delay and loss may occur due to the input buffer overflow, and in the output port, queuing delay and loss may occur due to the output buffer overflows.
Buffering when arrival via switch exceeds output. What? Because these are still in line. is the loss due to output port buffer overflowing. Is that because of the green isn't here? Why drop arriving tail? Why would they call it tail drop?
So in both the points, delay may occur. Alright, the last topic of this week's lecture that we are going to talk is IP protocol, Internet protocol, quite a huge.
See, she just kind of skips over this packet scheduling, priority scheduling stuff. Which I know will be on the exam for sure. So let me see here. Packet scheduling, deciding which packet to send. Which packet to send next on link. First come, first serve. That's what first in, first out basically. Oh yeah, first come, first serve. That's right here. Packet transmitted. Oh, this was the shit that when I did the interactive problem didn't make sense because it just didn't. Alright. And then priority scheduling. Yeah, this doesn't make sense to me.
Huge topic. We are not going to
I'm gonna have to ask him this for sure.
finish it in a single day or a single lecture. Rather, we are just going to talk about datagram format in this. Let's understand first of all the IP layer components. Okay, so the IP protocol we are going to discuss in this section. Routing protocols. Routing protocols determine the path a datagram follows from source to the destination and help in finalizing or selecting the path of the datagram. Then ICMP, Internet Control Messaging Protocol. It's a protocol, a facility to report the errors in the datagrams and respond to a request for certain network layer information. This week you learned about ping command. So ping command belongs to the ICMP protocol. The protocol related to the ping command is ICMP. So the basic purpose of the
ICMP, motherfucking PIMP. Alright, I don't think we're there yet.
ICMP is to report the errors and to respond to the request for the network layer information. Alright, so if you see over here, the network layer is a huge layer and it lies between the transport layer and the data link layer. There are many protocols, routing protocols for the path selection. We are going to talk about this. IP protocol for it does addressing. It is related to addressing datagram format, packet handling conventions. Then we have ICMP protocol. It is related to error reporting, router signaling. Routing protocols also help in making the forwarding table. So a very huge layer and many functions. Alright, so let's first of all talk about IP datagram format, just like we talked about TCP segment we talked about. So the size of IP datagram format is 32 bits. We know that the size of our IP address is 32 bits, which makes it 4 bytes. Now, what are the various fields in those 32 bits or in those 4 bytes? If you see, the first one is the version. Version tells us the version of the IPv4, and the version uses 4 bits. So 4 bits are used by the version. For example, IPv4 or IPv6. Then is the header length. So the header length, because IPv4 can contain variable of number of options, so again header length is 4 bits. These 4 bits are needed to determine where in the IP datagram the data actually begins. So header length tells us the number of bytes of data which this IP header is, which this IP datagram is carrying. Then is type of service. Type of service is used to determine the type of data it is carrying. For example, it might be useful to distinguish between real-time datagrams or those used by IP telephony from non-real-time datagrams, for example FTP. So what is the type of data? Length tells us the total length of the datagram including the header length, right? So header length and length. Header length tells us the length of the header, whereas length tells us the total the total bytes of the, or the total size of the datagram. So this is the total length of the IP datagram. It tells us header size plus data measured in bytes. So this field is 16 bits long, which is 2 bytes. So the theoretical maximum size of the IP datagram is from 65 is maximum is 65,535. However, datagrams are rarely larger than 1500 bytes when they are being transferred, but the maximum size of datagram it can have is 65,535. Alright, so now we have 16-bit identifier, we have flags and fragmentation. These three fields, they have to do with what we call it as IP fragmentation. In the next slide I am going to discuss it, and the new version of IPv6 does not allow fragmentation. So all these are used for the IP fragmentation. Time to live, TTL field. Next is TTL field. You might have seen the TTL field in the ping command, right? When you use the ping command, there was some TTL is equals to 128. So what does this TTL means? TTL field is included to ensure that datagrams are not in the network forever. So remember we talked about round trip time in the transport layer. So this is similar to that. So this field is decremented by 1 each time datagram is processed by a router. So if the TTL field reaches 0, the datagram must be dropped. So before the TTL reaches 0, the datagram should reach to its destination. So when the TTL field reaches 0 and the datagram is still in the loop or in the router, it will be dropped by the router. In that case, the sender will have to send the packet again. Alright, so upper layer protocol. This is upper layer. So this field specifies what is the protocol used by the upper layer. It can have either TCP or a UDP. So this specifies the protocol used by the upper layer. Next is the header checksum. Header checksum is used to calculate the errors, detecting the bit errors in the received IP datagrams. So this field is basically for the error detection. Alright, next is 32-bit of source IP address and 32-bit of destination IP address, which you all are familiar, IP address of the source and IP address of the data. Next is options, which can be like timestamp, record route taken, list of routers visited. So these are the various options. Last one is data. Data is the actual user data which the user is sending. It is of variable length, or it can be typically a TCP or a UDP segment, right? So how much overhead? So how much overhead the IP datagram carries? IP datagram has, the header size of the IP datagram is 20 bytes, right? This all is 20 bytes. Alright, so IP header, the size of IP header is 20 bytes, and we learned in the TCP, when we were doing the TCP, the size of the TCP segment is 20 bytes, right? 20 plus 20 makes 40. This is a fixed that it will have, because header, IP header will be 20 bytes, TCP header will be 20 bytes, plus this size option will be variable, which is the users related to the user data or whatever the data user is sending. So TCP segment is 20 bytes, 20 bytes of IP header plus 20 bytes of TCP header along with the application layer message. So this is variable size, and all of this cannot be greater than 65,535. This is the 65. Maximum size of IP header. But in practice, normally the datagrams are not larger than 1500 bytes, because if we have too big datagrams, then routers will take a lot of time to process those big datagrams. So normally the maximum size is of the datagram is 1500. So 1500 means this is 20 plus 20, 40. 1500 minus 40. If the size of, for example, the length of the IP datagram, if I say,
we did this in, I don't know, is it this one, the dividing it? I feel like it's this chapter that we do it. I remembered at 1500. I don't know if it's this chapter or chapter 3. Alright, I forgot where I was at. We're here.
Say, if I find out, for example, the length of the IP datagram is 1000 bytes. Here in this field, in the length, if it is written 1000 bytes, I want to find out how much is actual data. So actual data is 1000 minus 40. Why minus 40? Because out of 1000, 20 is for the IP header and 20 is for the TCP header. So 1000 minus 40 means about 960 bytes is the user data, right? So this is how we calculate. Alright, now we talk about fragmentation and reassembly. Fragmentation actually means breaking something, and reassembly means joining back. So network links have MTU. MTU means maximum.
This is the issue now, because fragmentation. Here, it's completely skipped over some other the subnetting. Yeah, here it is. The 1500, yeah. Max, is this max transmission unit?
Transmission unit, the maximum amount of data that can be carried by data link frame. Different link types, for example, a router will, a copper cable will have different MTU, fiber optic will have different MTU. So different link types, they have different MTUs. Large IP datagram. So if a device is sending a large IP datagram, it has to be fragmented in the network layer. Fragmentation means if the datagram is large, it will be broken down into certain pieces. So one datagram may become several datagrams. So this is at the sender side. But when it arrives at certain point which has at certain link whose maximum transmission unit is greater, then these several datagrams can be recombined back. This is called as reassembly. So fragmentation means we are giving one large datagram, but when it comes out of a link, for example a router, it is 3 smaller datagrams, because the maximum transmission unit of that router or a switch may be lesser. So this is called as fragmentation of the datagram. And why we need fragmentation? Because the maximum transmission unit of different links are different. So the link may not be capable of sending a large datagram. That's why it fragments the large datagram into multiple smaller datagrams. Alright. Datagrams fragment can be reassembled only at the
We got 10 minutes left of this video. I'm so excited. See,
final destination.
this chapter seems pretty okay so far. Except that round robin, FIFO, and all that other stuff. The packet scheduling, queuing. I don't know about
Not
all that.
inside the router. So if the datagram is fragmented by certain link, reassembly is only done at the destination network layer, not inside the router. So inside the router, the reassembly cannot be done. So for example, in the previous slide, this datagram was divided or fragmented into small 3 datagrams. Now these 3 datagrams will be combined into as a single datagram only when they arrive at the destination. Now how it will be combined? IP header bits are used to identify the order related to the fragments and the first and the last fragment of a single datagram. So there are certain bits in the header which are used to identify the fragmentation bits. For example, if I go to the IP header over here, we have over here fragmentation offset, flags and 16-bit identifier. So these 3 fields are used for fragmentation and assembly. Alright, coming back. Okay, so we have an example over here showing fragmentation and reassembly. Okay, so let's understand this IP fragmentation and reassembly. Let's assume that a datagram, the size of the datagram is 4000 bytes arrives at a link, but the maximum transmission capacity of that link is 1500 bytes. So that means this complete datagram cannot be transmitted from that link as a single datagram. So it has to be broken down. Now how many fragments should be made out of this? So because the maximum transmission capacity is MTU is 1500, so 4000 divided by 1500, which makes 2.66, which is equal to 3 fragments. So that means 3 fragments should be made. Now note that out of 400 bytes, we just now discussed that size of IP header is 20 bytes, right? So out of 400 bytes, it is only 3980 bytes which contain the user data. Rest 20 bytes is the IP header. So the user data is 3980 bytes. So it arrives at a router and it must be forwarded from a link with MTU of 1500 bytes. So that means this has to be broken down, right? So one large datagram now will become the 3 smaller datagrams. So how it will become the 3 smaller datagrams? The first length, of course, we will first of all how it will be broken down. So first length will be equal to the first length of the first datagram will have the maximum length of the equal to the MTU capacity.
One thing I don't understand is I thought hold on. I thought yeah, we're gonna have to go back over that other stuff. Alright, let's go over this real quick. Subnetworks, and that's this thing here, subnetting. So what is this? 23. 32 minus 23 is 9. Our maximum is 2 to the 9 minus 2, which 2 to the 9 is 512. Minus 2, which is 510. This one, what's this one called? Subnetting address. So yeah, the 32 minus 25 is just 7. Wait, so we'll need at least 92 characters, or addresses. The least number that bits to satisfy this is 2 to the 7, 128. Knowing that, we take the prior subnet and add 128. Which is, what is the subnet address of? Why does this become least number of bits that satisfy this is 2 to the 7. Because isn't 2 to the 2 to the 6 64? Yeah. So, okay, so that's how it, for A. Okay. 0, so subnet ID, broadcast address is always, the fuck? Subnet address, A, the broadcast address is 0. Wait, so we do 25, okay. Of subnet A is because of the last, yep, that makes sense to me. The first IP address, the ending is 126. This all makes sense to me, that's why I'm kind of skipping over it. The subnet of B, 2 to the 6, 64, because it needs at least, oh wait, that's B, needs 49. Because we are at B, we go in A, so 64 plus 128, what was that, 192? So, what is subnet address? Okay, that's the starting. So that's 191, alright. So that means this will be the subnet of C, will be 192, right? What is the starting? The ending? Yeah, 192 and then 27. Because this is 32 minus 5 is 27. The first, and yeah, this is all self-explanatory. The logical subdivision, yeah, that's pretty much it. They're addressed with an identical most significant bit. There was something that was skipped over too, the longest prefix. So I'm gonna go back to that. Before subnetting, after subnetting. Remaining low order bits, what's a subnet? Without passing through an intervening router. Pass through each other without an intervening router. Okay. Detach each from its host or router, creating islands. Islands. Detach each from its host or router, creating islands of isolated networks. Okay. What are the /24 subnet? There was a question, hold on my quiz that I wanted to figure out real quick. IP432, because IP6 is 128. This is because we do 32 minus 28, which is 4. 2 to the 4, which is 16, minus 2. When routers capable of network address translation. Oh, we didn't get here yet. Yeah, I thought this was 40. Was it this? I could have sworn there was a different question in regards to this number right here. Okay, IP addressing, class list, interdomain routing, CIDR. How does one get one? Don't you have to ask your system configuration? Dynamic host configuration protocol, DHCP. Oh yeah, she goes over this, but it's separated. I don't know, the slides are mixed matched here. Because this is still up here, I believe. Yeah, wait. Oh wait, TCP is 20. The overhead is 40. Okay. Where the fuck am I at in my notes? Yeah, I'm here. Alright.
Of the link, which is 1500. 1500 means the user data is 1480. I'm not going to talk about 1500. It will be 1480. Right? Identification can be anything. Fragmentation flag is set to 1. That means there is one more fragment of this IP datagram. Offset is 0. Offset means data is inserted from the beginning of byte 0. That means beginning of 0 the data has been inserted. So first 1480 bytes of the data have been inserted. Now let's come, because there is another datagram. So next 1480 bytes are inserted over here. Alright, so offset 1, fragmentation flag 1 means that there is one more fragment. Offset 185 means that data should be inserted at the byte 1480. It should be inserted beginning at a byte 1480. So out of 3980, 1480 are done. Now from beginning of 1480, the second datagram should start. This is the meaning of the offset. So how this offset is calculated? 480 data already has
I understand all of this. The 185.
so
Wait, actually,
the
where does that
fragmentation
185 come from?
at a byte 1480. So out of 3980, 1480 are done. Now from beginning of 1480, the second datagram should start. This is the meaning of the offset. So how this offset is calculated? Each byte has 8 bits. When you multiply 185 with 8, you get 1480, or you
Oh, that's how you do it. Why is this room so dark? I don't get it. And I have a headache.
you divide 1480 by 8, you get the 185. So this is how the offset is calculated. So next we still have one more datagram, because the fragmentation flag is set to 1. Now how this will be calculated? So 1480, 1480 have already been done. So out what was
Alright, I understand all
14?
this.
Next was 1. Offset is 370. So this is fragmentation is not set.
Alright, that's that video. Oh wait, I got quiz 2 here. Was it? I can't remember. Alright. Second video. Let's go.
Covered many things about the network layer, like we had introduction, we talked about what is inside a router, and then the last thing we discussed was the datagram format for the IP protocol. IP is a very important protocol of the network layer. Now in this week we are going to cover these three subtopics of the topic 4.4, which is
What the hell?
IPv4 addressing, ICM.
There was something yesterday. Let me try and think if I can remember it. It's the... It has... Was it direct feedback? Is that end to end? And then the one that has... Oh, it did. Wait, it doesn't have direct feedback. I think it's end to end. And then... Was it network assisted control? No, network assisted protocol. No, network assisted control has direct feedback. Or something about direct feedback. And then...
and IPv6. Although DHCP protocol will also be included in this. Alright, so let's start with this. We have already discussed about the IP addressing in our lab class, and all of you are already familiar, but still we will have a small discussion on it. We know that IP address is the unique address of the connection link. So the one on you can have a own IP. to much get over here. Okay, so interfaces are connected, wired interfaces are connected by the Ethernet switch. So we have done in the lab also. This is a switch. If we are, this is present in our lab also. If we connect,
Yeah, she's basically just going over this stuff again.
the wired interface, all the systems will be connected through the switch, and then this switch is connected through the router. So if we are using some Ethernet link or the wired link, it will be connected by the Ethernet switch. Wireless are connected by just the routers. So wireless links, they are just connected with the help of the wireless routers. For example, you can see over here wireless routers. Alright, now coming to the subnet part. Now IP address has two parts. One is the subnet part and another one is the host part. So subnet part is the high order bits and the host part is the low order bits. If I go back here, now these are high order bits and these are low order bits. So subnet part is defined by the high order bits and the host part is defined by the low order bits.
Subnet's high order, host is low order.
What is a subnet? Subnet is multiple devices having the same subnet part, but they have the different IP addresses. For example, I have an IP address 10.10.10.1. Then I have 10.10.10.2. Then I have 3, 4, 5, 6. So these are the multiple devices which have their subnet part same, but their host part, that means the machine number, is different. That means they differ in their IP addresses. It can physically reach each other without getting the help of the router. So all the devices which belong to the same subnet, they can reach each other and they do not require the help of the router. So for example, in this figure you can see that the systems having the IP address 223.111.112.113, they belong to the same subnet. So if they want to send message to each other, no need for the router. Similarly, the systems over here in the subnet 223.129, they have the IP addresses 223.121 and 122. They belong to the same subnet. So this is a example consisting of the three subnets. This is the one subnet, this is the second subnet, and this is the third subnet. So there are three subnets over here, and if you see over here, the each interface of the router has the separate IP addresses. So three subnets are created over here. Now to determine the subnets, how to determine the subnets? We will detach each interface from its host or router, creating the islands of the isolated network. So if you detach each of the host and if you create the island like this of the isolated networks, you get the number of the subnets. So for example, over here and over here we have the three subnets. Each isolated network is called as the subnet. And if you see what is the subnet mask over here, this slash number at the end is called as the subnet mask. Now let's look at it over how many subnets are there, right? So how many subnets? Of course, visible subnets. What I can see, I have over here the first subnet, right? Then I have the second subnet, which is this one. Then I have the third subnet, this one. I have total 6 subnets over here. Now how 6 subnets? These are the first 3 subnets. So the first subnets are 223.113 on the router interface. Then I have over here 223.126. Then I have 223.1.327. It has 2 systems, subnet 1, subnet 2, subnet 3. Subnet 1 has 3 computers, subnet 2 has 2 systems, subnet 3 has 3 systems. Now if you carefully look at the router, this router has three other addresses also, right? This has one address over here, one address over here, one address here, here and here. So if you see, that means it can create one more subnet over here. For example, at this interface, this is created at this interface. The subnet created at this interface between the router 223.192 and 223.191. So let's name it router 1. Let's name it router 1, router 2 and router 3. So the subnet created between the addresses 223.192 and 223.191, 223.191 between the routers 1 and 2, which is the fourth subnet. Then there is the fifth subnet created over here between the router 2 and router 3. Then the sixth subnet created in between these addresses. Between router 1 and router 3. So total number of subnets are 6 over here. So to determine the subnets, we detach each interface from its host or router. We create islands of isolated.
Hold on. You know what we should do? Let me get the interactive. That's what I should have done for the first video. Because this video's so boring. Alright, we're on chapter 4. She didn't really go over the longest prefix, but this one is kind of self-explanatory. To which datagram would this go to? Definitely go to 101. Oh wait, do I put... go to 4. 001 would go to 5. 000, that'd be otherwise. That's how easy this one is. Is the address space public or private? See, like a question like this is like, how do you fucking know? I guess private. How many hosts can be in here? 2. What? Oh, it's so 32 minus 24, which is 6. 2 to the 6 is 512. Wait, no, 2 to the 6 is... Fuck, what is 2 to the 6? Is it 64? It is, so this would be then be 62. Wait, no, it's 2 to the 8 minus 2. 2 to the 8. 256, so this would be 254. What is the subnet of A? 78. 2 to the... 2 to the 5, nope, 2 to the 7, 2 to the 6, so we need 2 to the 7, so 32 minus 7, 125, so it's going to be 218.111.1.46.0 slash 25. What is the broadcast? It's going to be 218. The broadcast, is that not Well, would it then be the 128? The last IP, so that would be the 7. What? 218.100 point. It was 2 to the 7. Oh, would this be 125? Bro. Oh. To 108.100.146.128. No, it's 127. What? Oh, isn't it this? I have an aneurysm. If it's... How do I get rid of this? So it'd be 126. The subnet of B. Alright. This is gonna be 2 to the 5, right? Wait, no, it's gonna be 26. Oh wait, no, it's gonna be... What? The 128... Bro. 128 subnet is the... Oh my god. Wait. Oh my god. What's this other one? Yeah, this other one, I have no idea. I'm gonna end my stream here. My brain burning. I can't do this.